Hey guys, welcome to this video on determining the electric field for a ring of charge. We're going to jump right into it. We're looking to find what the value of the electric field is at this dot that's marked at Z units away from a ring of uniform charge density with a radius of R. I'm also going to give a few more pieces of information. We'll say that the charge of the ring is Q and it's a positive Q value. So the first thing that we're going to do here is just take a look at what the direction of the field will be based on this ring of charge. So if we consider the ring as being a whole collection of independent point charges, we could think about each point charge affecting this point up here. So I'm going to just pick this point right here on the left, and what I'd do is I would say that that point charge is going to be creating a field that at the point shown will be directed up to the right, as we see here. And then every other point on here will do something similar in the corresponding direction. So I'm going to pick this other symmetrical one as well and try to draw a straight line here. We'd have something that looks like this. And because they're all equidistant, all of the point charges that make up this ring are equidistant from the point at location Z, we're going to end up with equal magnitudes and just a whole bunch of directions that oppose one another. So if we looked at just the vector perspective of this, we could see that the y components will add and the x components of this vector will cancel. So these will cancel out and we'll be left with just y components. Now I'm going to just put a few other reference labels on here. Let's call this angle phi over here, which would make this one as well phi. And we could then say that the cosine components are the parts that will not cancel out. So essentially what we'll be saying here is that the electric field is going to be some component of the total field lines added together. That's going to be a cosine component. So I'll just put a note here as we get ready for this. At this point, we want to take the definitions and the procedure that we set up in the introduction to more complex electric fields. So what we're basically going to say here is that every tiny little point charge, if we make each of those infinitesimally small, we could call each of them a value of dq. And each value of dq is a distance r away from the point that we are analyzing. And each of those dq values is going to make a dE component to the electric field. So again, we could write our electric field equation in this differential form as dE is equal to k dq over r squared. Now we've also shown that it's only the cosine component, so I'm going to go ahead and put here that each dE value, we are only really looking at the cosine component, and I'm using theta here again, but I actually used phi, so I should change that, and they're going to be equal to k dq over r squared times the cosine of phi. At this point, if we think about the idea of having a tiny differential contribution, that if I do integrate each side, I could get the total value of the electric field at that point. And so on this side, what I'm going to end up with is integral k dq over r squared times the cosine of that angle. It's also going to have to go from some limit to some other limit because we have a definite shape here. The issue is that we have too many variations that are occurring. Now this R value is actually fixed no matter which dq we analyze along the circle, and the angle phi is also the same, it doesn't change. The problem is that our variable of integration has to do with charge right now, and these things have to do with geometry of the perspective. So I'm going to now make a change from dq to something that has to do with the scenario at hand. So Because this is a line of charge that's just bent into a circle, what I'm going to say is that the linear charge density is equal to the total charge divided by the total length of that ring, which would be essentially Q over 2 pi uppercase R in this case. Now, if I want to write a differential form of this, I'm going to say that the total charge is equal to lambda times, I'm just going to put L in for now, just to keep us with less variables. And I could rewrite this as dq equals lambda, and I'm going to put here ds for an arc length. So the total circumference is now been broken up into little arc lengths. So I can replace the variable of integration here by doing the following. So the integral of k lambda ds over r squared times the cosine of phi. Now, to relate the angle to r, I'm going to make some substitutions that will be in terms of constants here. So if I look at r here, I can see r is going to be the same as big R squared plus z squared to the 1/2, or the square root of that. So big R and z are constants in this case. We can also write an expression for the cosine of the angle, which is going to be z over little r, which could be rewritten as z over the expression that I found for little r, which is big R squared plus z squared to the 1/2. So I'm going to make, again, more substitutions into my expression here. So I'll have integral k lambda ds, and now r squared is going to be, or r is going to be substituted in. So I have r squared plus c squared to the 1/2, and that's all squared. Okay, so then that would get rid of this square root. I then have to multiply by the cosine of the angle, which I have an expression for here. So then all I'm going to do is just substitute this in, z over r squared plus c squared to the 1/2. So little notes here, this square, okay, is going to eliminate this, but this one is not squared, right? So we have to keep it the way that it is. Okay, let's do some simplifications and rearranging here. So I'm going to move down here, and I'm going to put, okay, let's do integral k lambda z. So I'm just multiplying this out. I'm going to leave my ds out to the side here, and I'll show you why in a second. Now I have to multiply the denominator here, so I have r squared plus c squared times r squared plus c squared to the 1/2, which will end up being r squared plus c squared to the 3/2, and I'm going to put my ds out here, just to get it in a form that I'm used to seeing when I do an integration. Now, this looks complicated at first glance, but it's actually all constants here. K, lambda, z, r, and z are all constants. So I'm going to pull them out of the integral, and I will put everything out here and then see what I'm actually going to be integrating, which is very simple in this case, and that's just 1 with respect to the arc length. Now, I haven't been putting any limits of integration at this point because now I'm finally ready, and really when you think about it, I'm integrating over tiny little arc lengths from 0 all the way to 2 pi r. So if you're thinking about how the integration will occur here, I'm going to go from, I'm integrating 1 with respect to arc length, so I'll get just an arc length, and then I can plug in my upper limit minus my lower limit, which would just be my upper limit. So I'm left with k lambda z over, or times 2 pi r over r squared plus c squared to the 3/2. Now, one last step here, just to simplify this out, what I'm going to do is I'm going to substitute in lambda that I had from before, which was q over 2 pi r. So I'll end up here with k times q times, sorry, I left out my z, 2 pi r over, there's the other 2 pi r that came from my substitution, times r squared plus z squared to the 3 halves. Okay, now we can factor out 2 pi r, and we're left with k q z over r squared plus z squared to the 3 halves. So this would be an expression that I would have for the electric field at that point z. Now, what's interesting is if you think about as z becomes much greater than r, then the equation, so we could say basically as z becomes much, much greater than r, the equation goes to being E equals kq over r squared. And that is the equation for a point, or a point charge, if you will. So essentially, when you move really, really far away, you're really just seeing the ring as a single point, and that actually makes sense, because if you think about looking at a ring really far away, it might look like a dot because you're so far compared to the radius of the ring. Now, of course, if the radius of the ring was quite large compared to z, then this would be affected accordingly. All right, in the next video, what I'm going to do is take a look at, well, what if this were a disk of charge now rather than just a ring? How could we come up with an expression? And we're going to pick up from this expression that we have here. And so it would be helpful to jot it down to take to the next video.